All right, this video is going to walk you through how to solve proportions involving linear, area, and volume scale factors. The other thing you're going to be able to know how to do is how to convert those scale factors into the others so that you can work with common units in your proportions. All right, for starters, you've already worked with shapes like this before that are similar. When you work with similar shapes, you want to match your sides up, and you can make proportions out of those. If you were to go small over big, you'd match your 10 and 40 together to say 10 over 40. And if I'm going small over big again, I would say 3 over x. Now, to solve a proportion, you already know that you cross multiply and you divide by what's across from the x. But you can also notice that this side's dimensions on the one on the right here are 4 times larger than the one that's on the left. So if you just knew that this is 3, if you multiply that by 4, you'll get the answer of 12, simply by just noticing how much larger the sides are on the new shape compared to the old shape. And then you can also use, like I said, your cross multiplying skills, and 3 times 40 is 120. And 120 divided by 10 does also give you 12 as well. So if you want to use your proportion solving skills or recognize the scale factor of how many times larger something is, you can find them both pretty easy either way. Next, let's look at solving this next one that has 2 rectangles where you'll notice I've got 3 for this side and I got 6 for that side. So you can start by making your proportion that says 3 goes with the 6, the 4 goes with the x. And as you solve this one, you can recognize, hey, that 3 goes to 6, that's 2 times larger. That would then mean that this x has to be 8. So then if you solve that, you get x equals 8. Or if you just want to solve with your cross multiplying skills, 6 times 4 divided by 3 also gives you 8. All right. So in other words, though, I hope you're recognizing these 2 shapes that the linear scale factor to get from one dimension to the other dimension is all you're doing is just multiplying the original dimensions by 2. So your linear scale factor is 2. Now, let's compare the areas. Since this linear scale factor is a scale factor of 2, what's the area of this shape on the right here? Well, it would be your assumption to think that, well, if there's 12 here, this should be an area of 24. However, be careful. We said that these dimensions are 2 times larger. If it's 3 right here and this goes to 6, this is 4 on this side right here, which then means that this is going to be 8 right here. So if I've got 6 rows by 6 columns by 8 rows of squares, I would have 48 for my area here. So if that area is 48, you'll notice, hey, it's not as simple as just doubling the area. You have to actually take it by a scale factor of 4 instead. We're going to start to pay attention to these relationships as you go from linear scale factors to area scale factors. All right, now, exact same shape, drawn now 3-dimensionally. It has a linear scale factor that's 2 times larger. Hopefully you notice that. And then you're talking about the volume. If I count the cubes that are in there, there are 12 cubes total. Now, as you double the dimensions of this new shape right here, where they're all twice as high and twice as long and twice as wide, now, how many cubes do you have now? And if you count them all up, you're going to get a total of 96 cubes. So now, you'll notice that that also is not twice as large. It's actually 8 times larger. So this area, or this volume right here, ends up becoming 8 times as much as you started with for your original volume. So you'll notice now we've got 3 kinds of scale factors. We've got linear, area, and volume. Hopefully, eventually, that you will find the relationship of how you get from a linear to an area and how you get from a linear to a volume. Here's the next one. Another shape, but it's now got a scale factor of 3. You'll notice that everything in there is 3 times larger. So if I've got 3 getting multiplied by 3 to get 9, then you multiply 4 by 3 to get 12. So that means this is 9 by 12. Okay, so that means the scale factor then is going to be 3 times longer, just comparing the lengths of the sides. Now, compare the next one. If I'm going to compare areas, we know it's not going to be 3 times larger. If you actually compare this and work it out, you're going to have 9, like I said, by 12. 9 times 12 is going to give you 108. So the area now of this new one is actually how much larger? Well, let's compare that. If you take 108 and divide it by 12, the answer you get is 9. This scale factor of getting from this original area 12 to the new one is a matter of you multiplying it by 9. All right, well, now let's think about that for a minute. How could you turn a linear scale factor into an area scale factor that's supposed to be 9? Keep that in the back of your mind also. All right, now go to the next one here. We're going to talk about volume. The volume of this picture, if it's 3 by 4, is going to have 12 cubes inside of it. That means the volume is 12. As you look at this new shape, if you were to take all the dimensions and multiply them by 3, you'd have 12 by 9 and then also a stack high that's 3 stacks high. Well, we know that if you go 9 times 12, there's 108 cubes in this top layer, but you got 3 layers. If you take 108 times 3, you get 324. Now, how much larger is 324 than 12? let's divide that out. If you take 324 divided by 12, you're going to get an answer of 27. Okay, so now we're starting to see some patterns here. This one goes 248. This one goes 3927. I hope you're starting to see a pattern. Take a quick moment here to look at those and see what you think. All right, keep moving on here. Hopefully you're recognizing that if you take the original number of the linear scale factor and you square it, you will know the scale factor for the area. If you cube that original scale factor, you'll have the volume scale factor. So I can jump then from two figures that are the exact same thing. If I know what the linear amount is, I just cube it, and that'll be what I need to multiply the original volume by to get the new volume. All right, so let's check that out and see how that works. Here's a picture. It goes 1, 3, 10, and now it says for the new bigger one, it's going to be 5, 15, 50. How much larger are the dimensions of this picture? Well, look at it. They're 5 times larger. And that would then tell you then, what would the area of this shape have for, if I knew the surface area of this whole entire prism right here, then how much surface area, more surface area would you have here? Well, if you square the 5, it'll be 25 times larger. And if I talked about the volume of this shape, if I talk about the volume of this shape and I say, what's the new volume of this one over here? If the linear scale factor is 5 times larger for the dimensions, well, then you cube 5, which is 125. So the original volume of this, which is going to be 1 times 3 times 10, which would be 30. You just take 30 times 125, and you'll have your new volume of this larger shape. So just knowing how those relationships work out can make these problems easy to solve. Now, when you're looking at ratios, if I were to compare the ratios of the linear values, that's 2 times larger, or a ratio of 5 to 10. The ratio of my areas are 50 over 200. You'll notice when I'm working with these as a proportion, they are not equal. 50 over 200 is not going to be the same ratio as 5 over 10. This ratio reduces down to 1/2. This one reduces down to 1/4. Well, wait a minute. Think about that. Remember when you're supposed to square the linear? If you square 1/2, you do get 1/4. But these two fractions are not equal. All right. So let's talk about then, how could you make them equal? Well, if I square this ratio here, I could then compare areas, right? I could square 5/10, and then that would also then equal this exact same fraction that 50 over 200 reduces down to, which we already said was 1/4. So as I do that, I get 25 over 100, and then those two fractions, you'll notice, reduce down to 1/4 and 1/4. So you can take a linear scale factor. If you want to set it equal to another area ratio, you have to then square it in order for it to compare with what we're working with in the area ratios. All right, as you look at this one, if I were to make a scale factor out of the linear values and the area values, it would look like this. I'd have 2 goes with 10, and then 100 goes with my mystery, I don't know, I'll put an X there for the other area. Now, these two fractions, like we just said, are not equal. Okay, if we're going to make them equal, you have to square the linear scale factor. So if I square that ratio, I can now use this new information to solve as a proportion. If I square 2, I get 4. If I square the 10, I get 100. Comparing these shapes' values now, comparing the units, now that the units are measured in meters squared to meters squared, I can now cross multiply and solve this proportion. So take 100 times 100 divided by 4, and you'll get the answer of 2,500. Now also, this is not the way you have to do every one of these. You might already know this, that if you saw that, hey, this is 5 times larger, then I know in the back of my head the area scale factor is supposed to be 25. If you take 25 times 100, that also gives you 2,500 meters squared. So if you know the linear scale factor in the back of your head, by looking at the picture, it's not going to always be obvious, but if it is, you can just square it to know that how many times larger the area is supposed to be, and that'll make this easy to do also. Now the last thing is, let's look at some volumes. Here are 2 hexagonal prisms. The linear scale factor is going 6 to 18, which means that this shape right here is 3 times larger than this one. But as you put it into a proportion, if I were to go big over small, I could say 18 over 6. Well, if I'm going to go big over small in the volumes, I would say x over 200. Now, looking at these two things, you'll notice the units are not the same. And we also know that those ratios should not be the same either. But I can take a linear scale factor and cube it, and it would equal this scale factor over here as well. So what I'm going to do now is I'm going to say, hey, take the 18 over 6, and let's cube that. Now that ratio can compare with the ratio of my two volumes. So if I cube 18 and cube 6, I'll get a new ratio that looks like this. And then I can cross multiply and solve by taking 200 times 5,832 and then dividing by 216. As you do that and solve, you'll get an answer of 5,400 feet squared, or cubed, or cubic feet. You can also get that same exact answer really easy by recognizing, hey, wait a minute, this scale factor has a linear scale factor of 3 times larger. Well, I know it's not going to be 3 times larger for my volumes. I'm supposed to cube the number 3, which is 27. 6 times 27, try that in your calculator. It'll also give you 5,400 cubic feet. So knowing the ratios between two shapes, you square them for area, you cube them for volume, and hopefully that helps. Now, one little extra side note is if you have shapes that involve weight. Weight ratios are associated with the volume also. So that means if I know the ratio, this thing being 2 times larger, then if I'm talking about volume, I want to cube this scale factor of 2 times larger to be, if you take 2 cubed, you get 8. And then if you take 4 times 8, I already know the answer to this is going to be 32. Because if the scale factor of the linear scale factor is 2, and I have to take 2 cubed for volume, which is going to be 8, 4 times 8 gives you 32. But I'm going to do the proportion first. Let's set up the proportion by saying 8 over 16. And the ratio of the weights go from 4 over, I don't know. All right, so I can't say these are equal because I have to cube this ratio like I was just saying a second ago. So cube the 8, cube the 16. That turns into 512 over 4,096. As you cross multiply and divide, you get the answer like I just said, which is 32 kilograms. Again, you can see these answers pretty quick by knowing, hey, this is 2 times larger. When you deal with weight and volume, you have to cube the scale factor. So 2 cubed is 8, and then 4 for your weight of the original, then times 8 gives you 32 also. I really hope that we're making this easier for you as you start to understand these ratios. You cannot set the two ratios equal until you've cubed or squared the linear ratio. So here's what we got first. It says you have a ratio of similarity. When it says that, you can assume linear. So you have a linear ratio that's a 1 over 11. It may ask you in the homework also, what is the area ratio? Well, the area ratio is going to be, you have to square that original, and that becomes 1 over 121. So that means the area in the original compared to the original is going to be 121 times larger when you compare the areas. Now, to go on to the next thing, you have to set up a proportion. If you know that the area of the shape A is 27, and the ratio of this 1 to 11 is in a ratio of A over B, so that A is the small one and B is the bigger one, I need to set up my proportion like this and say 27 over X, because I don't know what the B value is yet. I'm going to try to find it, and that's going to equal 1 over 121. Notice that we're working with an area value for A. That means I had to turn my linear one into an area ratio before I could set it equal to my comparison of 27 over X. Now as you cross multiply and solve this one, 27 times 121, and divide by 1, you'll get the answer of 3,267. You'll see questions like that as well. So finally, to wrap this all up here, as you try to work with ratios, if you're trying to convert from one to the other, the one we just did today is dealing with linear ratios that get turned into area ratios by squaring them. If you start out with a linear ratio and you want to turn it into a volume ratio, you cube it. There are some problems eventually that you're going to be given the area ratio first, and you'll have to square root it first, and if you square root 9/25, it reduces down to 3 over 5. And then if you have to work with a volume ratio also, you could just cube it like you did originally. And also, lastly, if you ever start out with a ratio that's volume, you have to convert it to linear first by cube rooting 8 and cube rooting 27, which turns into a 2 over 3. And then you can then turn that volume ratio into an area ratio by squaring it. That's it. So as you try to now use these skills that we've been doing, try working on the homework or the classwork, the teamwork, and also the homework. Hopefully this video helps.